Hello everyone, welcome back to my channel. In this video I'll be explaining you regarding model laws, and in this video especially we'll be dealing with the Reynolds Model Law, and also we'll solve a numerical related to Reynolds Model Law. Okay, in my next video I'll be uploading regarding Froude's Model Law. Okay, yeah, coming to model laws. What are model laws? Model laws are also called as similarity laws or laws of similarity, which models are designed based on dynamic similarity. You remember dynamic similarity? Dynamic similarity is nothing but the similarity of forces between the model and prototype. So, these model laws define the similarity in between the model and prototype in terms of forces, which means I am telling it's a dynamic similarity. Then you should be thinking, why are we considering this Reynolds and Froude's? You remember this Reynolds and Froude's numbers are based on forces. They are dimensionless numbers which are derived from dividing inertia force with some other force. Means indirectly our model laws are talking about forces only. So dynamics, they are designed based on dynamic similarity, and since we are talking about dynamic similarity, we are including all the forces and the output, the whatever dimensionless numbers we have derived based on the forces, we are using them for designing the model laws. Okay, so we have totally 5 model laws which are based on 5 dimensionless numbers. For dimensionless numbers, you can just check out my earlier video. Right, we have the first one Reynolds Model Law, second one Froude's, third one Euler, fourth one Weber, and fifth one is Match. Out of these 5, Reynolds Model Law and Froude's Model Law have the utmost importance. So now in this video let's discuss Reynolds Model Law in detail. Let's see the scale ratios for it, and also let's solve a numerical regarding Reynolds Model Law. Right, so Reynolds Model Law, as the word itself, it is implying that this model law is based on which number? Reynolds number. So Reynolds number is nothing but the ratio of inertia force to viscous force. Okay, and especially this Reynolds Model Law is used when you design models based on Reynolds number, wherein you have the models regarding pipe flow, and also near models, designing the models of submarines or aeroplanes or immersed bodies. Why? Because there we have to consider the term viscosity in between the object and the water, or object and the fluid, whatever. So there is viscosity coming into action. So whenever there is viscosity or viscous force to be considered, we have to follow Reynolds number, and hence we have to consider Reynolds Model Law. Right, so as discussed earlier, Reynolds number is the ratio of inertia force to viscous force, and I have told you already, where viscous forces are predominant, we design models for Reynolds law. So remember blindly, wherever you get the term viscous force, or in between problems on model and prototype, wherever there's coming a term called viscosity or viscous forces, you should know you should get into your mind by default that it's Reynolds Model Law. Why? Because there is no other model law, there is no other dimensionless number which is having viscosity or viscous forces. Okay, so it should be Reynolds. So whenever you get dynamic viscosity or kinematic viscosity, get to a conclusion that it should be Reynolds Model Law, or regarding to Reynolds number only. So now I'll consider the model and prototypes for dynamic similarity. So Vm is the velocity of fluid in the model, ρm is the density of fluid in the model, Lm is a linear dimension. It could be length, breadth, or diameter, or width, whatever linear dimension of the model. Μm is the viscosity of the model. Μm means viscosity or dynamic viscosity, whatever. And obviously Vp, ρp, Lp, and μp will be the corresponding dimensions in the prototype. Okay, so according to our Reynolds Model Law, Reynolds number of the model must be equal to the Reynolds number of the prototype. Why? Because we are telling the dynamic similarity should be satisfied. So when you are telling dynamic similarity is to be satisfied, means indirectly that model law which is based on which dimensionless number, that should be same for model and prototype. So this model law is based on Reynolds number. So Reynolds number of model and Reynolds number of prototype must be equal. You remember the formula for Reynolds number which we have derived in my earlier videos, which is rho v L by mu. I already told you there, L means it could be any linear dimension. So rho v L by mu is the basic formula of Reynolds number. So for model means you should write all the suffixes with respect to m. model. So rho m Vm Lm by mu m is equal to Reynolds number of prototype, means rho p Vp Lp by mu p. This is the basic equation to be considered. This is our equation number 1. Okay, the basic equation, Reynolds number of model and Reynolds number of prototype are equal. So if I try to rearrange these terms, so I can write rho p by, means I will get all this right hand side to left hand side only, so that right hand side will be equal to unity. Then I will be getting like this. So rho p by rho m means rho r, Vp by Vm means Vr, Lp by Lm is Lr, 1 by mu p by mu m means 1 by mu r. So divided by mu r equal to 1. By, because rho r is rho p by rho m, as I've just told you. Rho r stands for what? Density ratio. Vr stands for velocity ratio. Lr stands for length ratio or linear ratio, linear dimension ratio, and mu r stands for viscosity ratio. Okay, next, this is the second basic formula you need to remember. First basic formula is this. Now from this basic formula of Reynolds number of model equal to Reynolds number of prototype, and the scale ratios regarding density, velocity, linear dimension and viscosity, we will write some scale ratios for other parameters. Suppose if we require the values of other parameters like time or acceleration or force or discharge for a model or a prototype, when one value is missing and the other value is to be calculated, then you can use scale ratios. Okay, now I'll teach you how to do scale ratios regarding models, Reynolds model law only. So TR is called time scale ratio, which is LR by TR, VR. Okay, why? Because we have velocity is equal to length by time, so from there time will be length by velocity. So R you are giving, means TR means it will be LR by VR. Remember this formula. Next, AR is acceleration ratio, which is VR by TR. Why? Because acceleration is velocity with respect to time. Next is FR. FR stands for force ratio or force scale ratio. The formula of force is mass into acceleration, so it is MR into AR. But MR is, we don't have any such term called MR or mass ratio, but we know that mass of the fluid is given by the formula rho AV. So we should write rho R AR VR into AR. There's a quite difference between capital AR and small AR. Capital area is area ratio, small area is acceleration ratio. So finally AR can be written as LR square. Why? Because area is product of two linear dimensions. So AR means LR into LR. So FR is rho R LR square VR into AR. Remember this formula. Next comes discharge ratio. We have the formula of discharge as rho into A into V. This is discharge per second. So QR will be rho R LR square into VR. Okay. So like this you have to obtain the scale ratios for discharge and force and also acceleration and also time. So why you use these scale ratios means, for example, if TR means what, actually time scale ratio, which is TP by TM. So if TP by TM value is given something value, then you can, if TP value is given, then you can calculate TM as that given value into TP. Like that, for the calculation of missing quantities either in model or prototype, you require the formulas of scale ratios. Alright guys, that's about Reynolds model law. Now let's see a numerical related to this. So see the question. Pipe of diameter 1.5 meters is required to transport an oil of specific gravity 0.9 and viscosity 3 into 10 power minus 2 poise at the rate of 3000 liter per second. Tests were conducted on a 15 centimeter diameter pipe using water at 20 degrees centigrade. Find the velocity and rate of flow in the model if viscosity of water is 0.01 poise. So see here, you have a pipe of diameter 1.5 meters, which is the prototype. Okay, the bigger value will be the prototype and the smaller value 15 centimeter diameter pipe will be the model. Obviously, right, prototype will be bigger than the model. So now let's start off writing the given data. Diameter of the prototype dp is given as 1.5 meters. Next, viscosity of oil. He's telling that in the prototype or in the big pipe of diameter 1.5 meters, he's telling there is oil flowing. Excuse. So viscosity of that oil is given as 3 into 10 power minus 2 poise. Next, rate of 3000 liter per second means discharge through the prototype is given, which is QP. So liter per second, I'm converting into meter cube per second. Just divide by 1000 or multiply 10 power minus 3. Next, Specific gravity of oil is given. So specific gravity of oil is given 0.9, but we don't require specific gravity in Reynolds number. We require density. So write density of oil rho p as S into 1000, 0.9 into 1000, 900 kg per meter cube. Next, let's write for model now. Diameter of the model is given, which is dm 15 centimeter, which is 15 by 100, 0.15 meters. Next, viscosity is given, means mu m. Why? Because through this 15 centimeter dia pipe, water is flowing. So viscosity of fluid in the model means mu m, which is equal to 0.01 poise, which is 1 into 10 power minus 2 poise. Okay, I'm not converting this poise into Pascal second. Why? Because both are poise and poise, right? If one is in poise and one is in SI system, I could have converted, but since both of them are in same poise, however it will get cancelled, that's why I'm not converting. Okay, yeah. Next, density of water is, we know it by default. Sorry, this is rho m. Okay, density of water rho m is 1000 kg per meter cube. So now according to our Reynolds number formula, Reynolds number of model must be equal to Reynolds number of prototype. If you remember this equation which I have told you to remember, the basic equation. So I've applied the same equation. So I have written Vm by Vp. Why? Because our one of the unknown in the question is find the velocity in the model. So Vm is missing. So that's the reason I am keeping Vm by Vp one side and I've sent all the terms on the other side. Why? Because you can observe all the other terms values are there for us in the given data except these two. Okay, I mean to say except Vm. So I've just kept velocity terms on one side and others are on one side. So I've substituted all the values. You'll get 3. So Vm by Vp we got 3. Remember this equation. But what is Vp? It is velocity in the prototype. Velocity can be given by the formula discharge by area. So Qp by Ap. But already Qp is given to us in the question, 3000 into 10 power minus 3 meter cube per second. Why? Because it was given as 3000 liter per second. I converted into meter cube per second, which is 3. Correct? 3000 by 1000 will be 3. AP, we don't know AP, right? Let's calculate. How do we calculate area of the prototype? Diameter of the prototype is given to us, dp 1.5 meters. So directly you can calculate AP by pi by 4 dp square. So now what did we get? Vm by Vp is equal to 3. Correct? Since Vm by Vp is equals to 3. Okay, so just keep this aside. So now let's calculate Vp. Vp is Q by Ap. So Qp by Ap. So 3 by Ap. So from here I got Vp as 1.697. Next, I told you Vm as Vp into 3. So 3 into this value, we got Vm. Our unknown is done. Next, he asked us to calculate discharge through the model also, rate of flow through the model. We have direct formula Qm is equal to Am into Vm. Am we don't know, so pi by 4 into dm 0.15 square into Vm just now we got. So you'll get the value of Qm. Okay, you got 0.0899 meter cube per second. Since discharge in the prototype is given liter per second in the question, let's write discharge through model also in liter per second. So multiply with 1000 you'll get. Okay, this is how we need to solve problems related to Reynolds model law. This was a very repetitive question I have solved, but here you observe in this question anywhere related to LRs, length ratio, or else anything related to scale ratios, QR or FR I did not use. This model of problem doesn't require scale ratios. Okay, so in the next video I'll be talking about Reynolds model law. There at a time I will be explaining you if how in the question the value of LR will be given and how to apply the values of LRs, that I will tell you in the Reynolds model law, so that I can cover you there itself. Okay, so hope you understood this video. Thank you.